All right, guys, we were on probability of dependent events. Yesterday, we did mainly independent. Today, we're going to do dependent. Maybe throw an independent in there just so you can see the difference in the two. All right, first of all, what is dependent? Dependent is kind of what you think it would be, just what it sounds like. If the occurrence of one event actually has an effect on the occurrence of another. So if one outcome is affected by a previous event. That kind of probability is called conditional probability. The probability that B will occur given that A has occurred. So the probability of B was changed because A has already occurred. That's because that's the condition or conditional. We write it like this, and the way we read it is like the probability of A occurring given that B has occurred. So when you see that line, it basically means given that B has occurred. All right, let's try 2 or 3 examples here, see how we do. Well, forget that for a second. Probability of dependent, here's how we're going to do it. Notice the word and is back with us. If the word and is with us, automatically means we're going to multiply. And we did that yesterday. The difference today is they're going to be dependent, which means something has happened to affect B, which means it's conditional. So what you do is you do probability of A, the first event, times probability of B, given that A has already occurred. So it's going to change the probability of B just a little bit because A has already happened. All right. The table below shows the numbers of tropical cyclones that formed during the hurricane seasons from 1988 to 2004. Use the table to estimate A, the probability that a future tropical cyclone is a hurricane, and B, the probability that a future tropical cyclone in the northern hemisphere is a hurricane. So the first part A is just asking you probability that it's a hurricane. That's basically all it's asking you because in the northern hemisphere. So sorry, that's the second part. That's a hurricane. So I'm going to count the total number of storms in the whole thing. I mean, northern and southern hemisphere, and I get 1575. And then I'm just going to count hurricanes only, which is this column, that row right there. Add those two together, get 760, and that's it. Or actually, it would reduce. Let's just go decimal and say it's 0.483. All right, so it's probably that is a hurricane with no conditions on it, just that it's a hurricane. Now read part B. Part B says the probability that a future tropical cyclone in the northern hemisphere is a hurricane. So that means I want the probability that it's a hurricane. I'm going to abbreviate hurricane like that. Given that it's in the northern hemisphere. Okay, probably a hurricane given that it's northern hemisphere. So that means all I'm looking at is this right here. I need to change colors, but all I'm looking at is this column because it says northern hemisphere. So how many storms in the northern hemisphere altogether? If you add those numbers up, you get 1142. How many hurricanes? 545. And if you do that decimal there, it's about 0.477. So I need you to see the difference in those two. Part A just says the probability that a future storm is a hurricane. So you add everything up. But part B is the probability that the future cyclone in the northern hemisphere is a hurricane. So it gave you the condition that it had to be in the northern hemisphere, which means I just looked at this part of the table, which means it was given that it's in the northern hemisphere. It's conditional. There's a condition there. All right, try another one. You randomly select 2 cards from a standard deck of 52 cards. What is the probability that the first card, I should say card instead of care, first card is not a heart and the second card is a heart? If A, you replace the first card before the second card. So that's saying this, probability of A times probability of B. But there's no condition there because you're putting it back. So when your second pick has no effect from your first pick because you're putting it back in the deck. So you still have 52 cards. So the way you'd work that one out is you would just say, okay, the chances of getting not a heart on the first card is 39 out of 52. Because you put it back, there's still 52 cards in there. Probably getting a heart the second time is 13 out of 52. And if you multiply those out, you get 3/16 or 0.188. Now the B part says this: what if you do not replace the first card? Now I have this probability of A of not getting a heart, and then probability of B given that A has occurred because you're not putting it back. So the fact that you did not put the card back actually affects the second drawing, which makes it conditional. So the probability of A is still 39 out of 52, but here's the difference. Now, to get a heart, there's still 13 hearts in there, but there's just 51 cards in there because you did not put it back. So if you multiply those two, you get 13 out of 68. Now, again, trying to get you to see the difference in that. Part A was independent like yesterday. Part B is dependent like what we're doing today. Got one more slide. All right, you and 2 friends go to the same store at different times. to buy costumes for a costume party. There are 15 different costumes at the store, and the store has at least 3 duplicates of each costume. What is the probability that you choose different costumes? All right, so basically that means you can all get the same costume because there's three duplicates of each one. So technically you could all 3 get the same one. So basically it's like this: probability of A times probability of B, given that the first person's already been in there, so it should be A, and then times probability of C, given that B and A have both been in there already. Okay, so it's big time on the conditions. So probably if the first person walks in, they can choose 15 out of 15. They're going to choose one. You can just put 1 there if you want to, but the first person, 15 out of 15 chance they're choosing one. Now, the second person, chances that they choose a different one. All right, the first person's already chosen theirs, so they have a 14 out of 15 chance of choosing something different. Still have 15 in my denominator because there's 3 of each one, which means they could pick the same one if they wanted to, but so there's still 15 choices. Third person still has 15 choices because there's 3 of each one, but it's supposed to know that they pick 3 different ones. So technically there's a 13 out of 15 chance the third person choosing something different from the second person and the first person. So you multiply all that out and you get and reduce it, you get 182 out of 225. If you change it to decimal, it's about 0.809. So that's dependent. That's what we're doing today. And tomorrow in class, conditional probability. Your second outcome is affected by what happened already. So hope that made some sense. See you in class tomorrow. We'll work them out like we always do. See you then.